vicious cycle of IT evolution and the rise of cloud complexity. The rise of virtual machines and networks. The rise of containers and pod networks. Cloud computing addresses how to make right resources available to right computation to improve scaling, resiliency and efficiency of the computation in a distributed environment. It attempts to automate and manage a. the computational workflow execution by placing the workload components in desired hardware, and b. the network of computing nodes to assure connectivity, availability, reliability, utilization, performance, and security, known as fault, configuration, accounting, performance, and security, gaps management, of the distributed application. The cloud management involves IP address-based virtual server management and associated virtual network and storage management. Therein lies the limitation as scale of deployed components and fluctuations in the demand for or the availability of resources increase. With multi-cloud deployment of workloads across large geographical distribution, reconfiguration of resources to meet the fluctuation demand reaches a limit, creating a complexity cliff or barrier. The complexity barrier limits the scale, resiliency, and efficiency as shown in this figure. As George Gilder points out in his book Life After Google, this complexity barrier is related to the limitations of current von Neumann implementation of the TM and the associated Church-Turing thesis, which states, a function on the natural numbers is computable by a human being following an algorithm, ignoring resource limitations, if and only if it is computable by a Turing machine. Resource limitations cannot be ignored when fluctuations in the demand for workloads such as the demand for pizzas increase by an order of magnitude within a short period of time during a Super Bowl game. Nor they can be ignored when some hardware components fail and disrupt a component of the workload execution. Resiliency of workloads at scale must address assuring resources at all times without disrupting the workload transactions at scale. March toward an IT where workloads matter. The problem of complexity, resiliency, and efficiency of workload deployment and management at scale is compounded with the advent of 5G wireless access to workloads and the Internet of Things. There are two drivers for rethinking workload management strategy. First, connecting people and things distributed geographically with different requirements at the edge requires a change from one-size-fits-all single-vendor multi-cloud strategy. Second, pushing computing closer to the data sources and data consumers increases efficiency. Cloud brings unlimited scalability and serverless automation. When edge computing meets required service levels, it is cheaper and faster. However, managing thousands of heterogeneous devices, and hundreds of applications for millions of users at the edge, is problem number one. Dispatching workloads in real time either to the edge, or towards clouds when needed is problem number two. The small video depicts the cloud bottleneck. As George Gilder points out, a new architecture for IT is required to address scale, resiliency, and efficiency, especially security and data governance. He says, the next era system of the world will see the ascent of memory and specificity, invention and factuality, timestamps and titles, what Chaitin, the great surviving information theorist, calls the new math of creativity, the math of human freedom that follows Gödel and Turing and their proofs of uncomputability and incompleteness. The universe is hierarchical and multidimensional. It cannot be reduced to two-dimensional sequences. Self-referential circularity of all logical systems not moored to reality outside of themselves. Security is not a benefit or upgrade that can be supplied by adding new layers of passwords, ponytailed SWAT teams, intrusion detection schemes, antivirus patches, malware prophylactics, and software retrofixes. Security is the foundation of all other services and crucial to all financial transactions. It is the most basic and indispensable component of any information technology. Here are the requirements for end-to-end deployment of workloads that manage information services connecting people, things, and businesses to communicate, collaborate and conduct commerce with resiliency and efficiency at scale. Requirements for deploying at scale are: hundreds of distributed service delivery points, thousands of services, millions of users, billions of devices. Requirements for resiliency are: non-stop service availability, hacker-proof security, global and local data governance, application service level assurance, SLA, independent of who is providing the resources. Requirements for efficiency are: end-to-end service visibility and control, workload placement to optimize efficiency, vendor agnostic and infrastructure agnostic service delivery and operation. As Mitchell Waldrop points out in his book on complexity, the edge of chaos is the constantly shifting battle zone between stagnation and anarchy, the one place where a complex system can be spontaneous, adaptive, and alive. Fortunately, a new generation of mathematics and a new understanding of information processing structures allow us to go beyond church-Turing thesis limits and address the deficiencies in improving resiliency and efficiency at scale. The major limitations of TM-based computing, besides the points already made by Gilder, are: a TM's underlying logic is a fully consistent standard logic. The TM is always assumed to be in a well-defined state. A universal TM is also a TM but with the ability to simulate a sequence of synchronous TMS, each execution with its own description. However, computations in an open multi-cloud environment, where the resources are managed by independent actors, have special requirements that go beyond TM capability. These computations are concurrent but asynchronous, and the computational logic must be robust enough to tolerate inconsistencies and adjust the global behavior with the knowledge of inconsistency. As scale, number of distributed computing elements involved in the business process, and fluctuations increase, the TM limitation becomes pronounced. A Turing machine requires adequate CPU and memory to execute the algorithms and stops when the resources are not adequate. Cognition is the ability to sense and predict the resource requirements and adjusting them without disrupting the workload transactions. If a workload is composed of asynchronous concurrently running sub-processes, and their relative behaviors fluctuate randomly, then the current computing model is inadequate. The recent advances in new mathematics consisting of named sets, knowledge structures, the theory of oracles and structural machines provide a way to implement a new class of distributed workload deployment and management that extend the scale resiliency and efficiency. This method does not impact the workload development processes but allows cognitive management of end-to-end computational processes and sub-processes. In order to model intelligence in the digital world, first, we need to go beyond the current limitations of symbolic computing by infusing cognition and sentient behavior to address fluctuations in the demand for, and the availability of, resources without disrupting the computations at hand. No shared storage required across multiple clouds. The theory of oracles and structural machines offer us a way to implement hierarchical cognitive overlay that allows distributed computations to manage themselves and their interactions with other systems and the environment with global knowledge and local control. Behavior in one component can be changed through message communication. Structural machines provide a framework to address computational functions, algorithms or tasks that can be described, structure and fluctuations by infusing cognition through cognizing agents to create sentient behavior. Implement hierarchical intelligence and 4E cognition.